So today's lesson is on the reactivity and natural occurrence of elements. Obviously, different chemicals are more abundant or less abundant than other chemicals on the Earth. So for instance, you see here gold. Gold was really abundant. Everyone would be wearing gold all the time. But we don't see that. Gold is quite hard to find. But things like nitrogen in the air, that's everywhere. Different elements and different chemicals appear because of their reactivity. And that's what we're going to be looking at today. For instance, in the gold example, we all think that gold is very precious or very valuable. But you may have thought, why? What makes gold more valuable than other elements? And the reason is because we can find it by itself. We can find it in the ground without it being connected to anything else. So it's gold. When we pick it up, it's just gold. And that is advantageous because we don't have to learn how to get the gold out of a rock. We just have to pick it up and then melt it down and make it into whatever we want. And that's part of the reason why historically gold has become very valuable to us, because we can find it. Similarly, you think about silver. Silver we can also find just like gold, but obviously it's more abundant, but we think of it as very precious as well, very valuable. I don't think of iron, which we have to dig and mine and then refine, as super, super valuable, but I think gold is pretty valuable. So you can see how historically our decisions about what is nice and what is valuable to us have been shaped by the chemistry. Not 100% shaped by the chemistry, but that's just one aspect of it. So just something to think about. So reactivity. Before we can look at natural occurrence and things like that, we need to have a quick and brief look at what reactivity is. Intrinsically, some elements or some chemicals are more reactive than others. And what does that mean? Well, it means that they want to combine or to reshape other substances or elements or chemicals when they come into contact with them. One typical example is, say, sodium. Sodium kind of reacts very, very strongly with water, and that's why you can't keep sodium just in air. You've got to keep it in some kind of oil, sort of non-reactive oil, because you need to keep the water away from it because it reacts really, really strongly. That's just one example of things being really, really reactive. Now, the reason why they're more reactive is because of the way the chemical is structured. So in chemistry, there are sort of two things to think about. One is, what is the chemical or substance actually made of? If it's a molecule or some other compound, we need to know what elements go into that compound. Or if it's the element, well, how many electrons does it have? How many protons does it have, etc. So there's one part of chemistry where we think of what is it made out of? The second part is how are those parts put together? So there are lots of chemicals that share the same chemical composition. So that is, they are made up of the same number of elements. So hydrocarbons are one example. You could have the same number of carbon, the same number of hydrogen, the same number of oxygen, but they're put together differently. So if they're put together differently, they have different properties. They do things differently with each other. There's two parts, what it's made out of and how it's put together. And in reactivity, we're looking at, well, there are instabilities in the way it's put together, which make it reactive. And the reason why it's reactive is because it wants to try and rectify those instabilities. It wants to try and fix them. And that's the driving force for reactions. So when we put two reactive chemicals together, we usually get really violent reactions. So if you look at the periodic table, if you take the element on the bottom left-hand corner and react it with the element on the top right-hand corner, both of those two chemicals are very reactive. But if you put them together, you get a really, really violent reaction. An explosion is a type of really violent reaction. And so that's what we usually get when we put chemicals that are very reactive together. Oxygen, the thing that we breathe, that's considered quite reactive because it reacts with iron just spontaneously. And it also reacts with pretty much every other metal on the planet, with the exception of gold and silver and some other things. So oxygen, the reason why we breathe it is because it is reactive. Because it reacts with things, it releases energy, and we know we have to breathe to kind of power our body. And so that oxygen can actually be used to generate energy. And so, I can go for a jog and other things, do other activities that require energy. On a more industrial scale, when we burn things like petrol, diesel, coal to produce some form of energy, like electricity or transport motion, oxygen isn't required because it reacts with the fuel to cause a fire, essentially. And that fire can then be used for various purposes, such as creating electricity. You can see oxygen is reactive. It does lots of things for us, and we exploit its reactiveness for our benefit as humans. There are elements that are reactive, and obviously there would be elements that aren't reactive. When we talk about chemical elements being reactive or non-reactive, there are some that have very, very low reactivity. One typical example of this is the noble gases. Nitrogen gas is another example of a very non-reactive element, but the noble gases are kind of the kings of non-reactivity. So if you were to grab a periodic table and then look at the furthest most right-hand column, it's the, say, neon, it's helium, argon, neon, those names all come up. Those ones are not reactive at all. They're just non-reactive. And we can find them all over the planet. We don't have to extract them, we don't have to dig them out of anything. They just exist by themselves. Here we've got a neon sign. I'm sure you've seen them around. They were a hallmark of advertising. It's just full of this gas neon. And when we pump electricity through it, this just neon, the electrons kind of smash into the neon atoms, and then some physics happens and light comes out. And that's why we have neon signs. It's just a tube full of neon gas with electricity passing through it, and it emits light. That's sort of similar to how a fluorescent light works. We have those noble gases, which are the kings of non-reactivity, but we also have some non-reactive metals. Lots of metals are reactive, but there are a few ones that we can see in nature and industry that aren't reactive. So we've got gold, platinum, and silver. Those are the three major ones. If you think about what those metals are, think about how much you value them. Gold, valuable. We like gold. Platinum may not be sort of that you use it all the time or that you've seen it, but platinum is really important in industry because it basically makes reactions happen for industry. Where you might have seen platinum, you may not have actually seen it, but platinum as part of your life is in your car. If you look at the exhaust pipe of your car, there's this kind of box thing just before the end, and that has a small amount of platinum in it to make sure that carbon monoxide doesn't come out and poison you. So platinum is important, but because it's also rare, trying to find new elements or new chemicals that can replace platinum in certain applications. But we can find it in nature just by itself. And silver, again, we think silver is good. We think silver is quite valuable. Because we could find them, and they're quite rare, these three chemicals, we value them. And that's just sort of economics 101. The supply is low, the demand, because we can find them, is high, so we value them a lot. You just have to think about that is part of the reason why we value gold very highly. What we call this family of metals that we find just lying around, we call them native metals. In other words, they don't react with things. We just find them in their base native form, and so we call them native metals. The noble gases and the native metals, they're sort of special exceptions in the periodic table. Most other elements in the periodic table will be found, or if we were to just go looking for them, we'd find them combined with other elements because they have much higher reactivity. Where would you find sodium in the world? I know an easy place. I'll go to the beach, the ocean. That's full of sodium, sodium chloride. Sodium chloride is salt. So you can see that sodium and chloride are bonded together. They're combined together in nature as salt, and we can find that in the sea. What about carbon? Well, carbon and oxygen are bonded together. They're causing problems in the atmosphere. Carbon dioxide. So you can see carbon and oxygen are bonded together to form carbon dioxide. If you're a mining fan, aluminium, that's found as bauxite, which is aluminium oxide. So you can see aluminium is bonded with oxygen. Most other elements in the world will be found combined with something else. Not necessarily oxygen, doesn't have to be oxygen. You can see in the sodium case, it's chloride or chlorine. That's just something to be aware of. What are the likelihoods of kind of finding a chemical by itself or finding a chemical bonded to something else? The way we look at that is, well, we say, look, well, what is the reactivity of that element? Sodium is very, very reactive, which means that it's very likely to be bonded with something else if I was to go looking for it. I might be able to find some sodium just miraculously by itself. It's possible. It's unlikely, but it's possible. Gold is completely unreactive. I don't expect to see gold bonded to anything else. It might be, again, by some very, very specific conditions, but it's unlikely. Argon or neon or any of the noble gases, I don't think there's any examples of ever finding that bonded with something else. That's because they're the most unreactive. You can see that the reactivity tells you how likely it is that I'd find it by itself or bonded to something else. So that's just a quick way to think about that. So the more reactive, obviously, the more readily it will form compounds, the less likely you are to find it by itself. Oxygen is obviously a very reactive gas, and it forms about 46.6% of our Earth's crust. So I'm not talking about the atmosphere, I'm just talking about the rocks in the Earth. It's about 46% of it is oxygen. That sounds pretty amazing because it's a gas, but you got to remember when it's bonded to things, it does different things, like it operates differently. So obviously, because it's so reactive, we find it bonded to practically everything. We find it bonded to iron, we find it bonded to copper, aluminium, all the stuff that makes up our Earth's crust. Silicon, the most abundant of the elements that's not oxygen, that is bonded to oxygen in the end of the day. It's silicon dioxide. What is silicon dioxide? If you go to the beach, scoop up some sand, that's silicon dioxide in your hand. You can see that oxygen is just everywhere in the ground. It's also everywhere in the atmosphere, but very, very prevalent in the ground. Oxygen kind of exists in many forms. It's silicate, which is what I talked about, the silicon dioxide. That's a silicate. Carbonates, so when oxygen is bonded to carbon, we call it kind of like a carbonate. Or in oxide minerals. A mineral would be something that we mine. So if we just kind of took away this RALS, it'd be mine. So a mineral is something we dig out of the ground to turn into something useful. Oxide minerals are just minerals with oxygen. So aluminium oxide, we use aluminium for cans and aircraft and stuff like that. We mine it as aluminium oxide. That is an oxide mineral. So quartz, for those who are up-and-coming geologists or interested in kind of crystals, quartz is composed of silicon dioxide. Why does that make it different to sand? It is basically the same as sand. The reason why quartz is a little bit, kind of value quartz a little bit more highly is because quartz is a slightly more pure version of sand. Sand has a lot of contaminants in it, and that's why it's kind of brown and more different colored. Quartz is usually white or clear because it has fewer impurities. So it's just silicon dioxide. That's why kind of the value system that we place on different things is kind of based on science. So that concludes today's lesson on the occurrence and reactivity of chemicals in the Earth. So we've looked at a very high level, what the chances of finding certain chemicals are based on their reactivity and why we have different reactivity levels. So in future lessons, we're going to really dig deep and dig into what are these instabilities that I talked about, what governs reactivity and things like that. But this was just an overview of kind of looking at what we're likely to see in the Earth and a bit of an explanation as to why. We can do some questions now to pull together that information and sort of show you what you can do with this information. So the first one is, which of the following is not a molecular substance? Remembering that molecules are combinations of different atoms. And how do they vary from compounds? Well, a compound is a combination of different atoms. A molecule of oxygen could be two oxygens stuck together, but they're the same. Two oxygen atoms are exactly the same. But say carbon dioxide is also a molecule, but we also call it a compound. So a molecule and a compound, they can vary slightly in the definitions. So which one's not molecular? Well, I just said O2 is a molecule. H2O, that's also a molecule, but it's a molecular compound. So we can find this individual chunks of water. When we boil it, we can turn it into a gas, basically. This is P4, it's a phosphorus molecule. And the reason why it's a molecule is, again, because we can find it kind of drifting around by itself. Now, the difference between a molecule and other substances is that you usually can find one group of them by themselves. You can isolate one group. But in a crystal, you can't really say, because everything's kind of stuck together, you can't really say, well, where does one stop and where does the next one begin? So in this case, water we can get as a single particle. Oxygen, O2, we can kind of extract and find one particle. Phosphorus 4, we can kind of find as one group just floating around. Now, if we look at a grain of salt, sodium chloride, how do you get one sodium chloride? Because if you looked at a crystal, you'd find sodium here, then chloride here, then chloride here, and then there'd be sodiums and chlorides everywhere, and it'd be kind of bonded in these, all these circles stuck together. There'd be sodiums and chlorides all stuck, interchanging. Will I be able to find just one sodium chloride? It's unlikely. We can't just take away one sodium chloride. That means that it's unlikely to be a molecule, and so that's probably our best bet for an answer. And as you can see, that is the answer. It's the only one that's not a molecular compound. It's clearly like a crystal of some description. So which of the following is different from the others? On a very high level, you can kind of just see straight away, this one has 2, this one has 2, and this one has 2. So that's one way to say, well, look, this one's different. But kind of on a scientific basis as to the answer of this question, well, this is a molecule of nitrogen, this is a molecule of chlorine, and this is a molecule of bromine. So they're all molecules. They're stuck together. 2 nitrogens, 2 chlorines, 2 bromines, all stuck together. This krypton, not to be confused with the Superman stuff, but krypton is an element, and it's by itself because it's a noble gas. If you looked at your periodic table, right on the right-hand side, you'd find krypton probably 3rd or 4th one down. Obviously, it exists by itself because it doesn't react. So each krypton atom just goes around by itself, hangs out in the gas, and that's all it does. So you can see that it's different because it's not a molecule. It's not two things stuck together. Okay, and that's our answer. So compare the reactivity of the metals magnesium and gold. Well, obviously we've talked about this. You may not know a lot about magnesium, but you definitely know a lot about gold. So you might have seen the magnesium experiment where you heat magnesium and it starts glowing really brightly because it's reacting with oxygen. So you know that it reacts with oxygen now at least. So magnesium is much more active than gold. We know that because gold is probably the least reactive metal. We readily find gold by itself. Ancient people used to dig out gold and then turn it into jewelry and things like that. But magnesium is rarely found as anything other than magnesium oxide. So it's very, very unlikely we'll find magnesium by itself. Now, obviously this shows that gold is far less reactive than magnesium because we don't find magnesium by itself. So explain the relationship between the reactivity of an element and the likelihood of it existing as an uncombined element. Okay, so I explained this quite a lot. I tried to push this point. A reactive chemical is less likely to be found uncombined. Very unlikely that you'll find it in an uncombined state because it just wants to bond with anything that it can find. So most elements are chemically active in some way, and so they occur as compounds or combined with other elements. The less reactive an element is, as I said, the more likely you find it uncombined. So that is just a product of chemistry. For example, the noble gases or inert gases, group 8, and unreactive metals like the native metals occur as elements. You can find them by themselves. You don't have to go looking and chopping and cutting molecules. So the Earth's crust consists of the outer portion, which is 40 kilometers thick. The most abundant element in the crust is oxygen, iron coming forth at about 5%. If the whole planet is considered, the most abundant element is thought to be iron, which makes up about 30% of the Earth's mass. Account for the difference in the abundance of iron in the Earth's crust compared with the entire planet. So in the Earth's crust, iron is combined with other elements to form minerals. Okay, so it combines with other things to form minerals. But the Earth's core is made up of almost pure iron and some nickel in there as well. So the Earth's core has a lot of iron in it, but the Earth's crust has very little because it's combined with other things. So if you looked at the whole mass of the Earth, that core makes up such a big part of the Earth's mass that it kind of throws our percentages out a little bit. So that concludes today's lesson on reactivity and natural occurrence. So hopefully you've learned what each of those parts, how they fit together. And in future lessons, we'll be talking about what reactivity is and how we actually can predict it. So thank you, and I hope you've enjoyed this lesson.